Hi, this is Smitty, and welcome to the JD Edwards 9.2 Lead Time Workshop. This is a recorded presentation of lead times for purchased and manufactured items. The purpose of this presentation is to build an awareness and understanding of JDE's lead time calculations and work order back scheduling logic. The intent of this PowerPoint presentation is to enable the user to do a self-guided tour and discovery of JDE's lead time concepts simply by reviewing and studying this presentation video at their own pace. Users are also encouraged to read and study JDE's Product Data Management Implementation Guide in Chapter 7 about item lead times. Here's an example of the JD Edwards Implementation Guides. Simply select Product Data Management, download the PDF, and in the table of contents, search for lead times. For advanced reading and study, refer to myOracleSupport.com for various white papers on the subject of lead times and back scheduling logic. Here's an example of my Oracle Support and a few of those white papers on the topic of lead times and back scheduling logic. Let's begin. All ERP systems and their planning modules rely on lead times. Let's first review the purpose of lead times and why they are needed. Determining lead times are an essential part of any manufacturing or scheduling process. For any product that you purchase, you encounter a lag time between when you order it and when you receive it. For any product that you manufacture, you encounter a lag time between when you start it and when you finish it. To account for the lag time, you must estimate a lead time and account for it when planning and back scheduling purchase orders and work orders. This is needed to determine when materials are needed, and this is needed to determine when jobs are required to start by and be completed by, and if they are to be made on time and when you promise them. Next, we'll review the JDE lead time concepts that are available for use. JDE uses two types of lead time concepts. They are fixed lead times and variable lead times. Fixed lead times are where an item's replenishment lead time is always based on a fixed number of days, regardless of the replenishment quantity. Replenishment lead time days for purchase items will always use the fixed lead time days concept. Using the fixed lead time days concept is optional for manufactured items. When using fixed lead times for manufactured items, the lead time to replenish the item is the same or exact number of days regardless of the quantity being manufactured. An example would be when manufacturing a lot size of 10 inches, 5 days is given for the manufacturing period, where a lot size of 10,000 inches is given the same 5-day period to manufacture the goods. As opposed to using variable lead times, where manufactured items replenishment lead time is variable and where it always takes longer to replenish larger lot sizes or takes less time to replenish smaller lot sizes. An example would be here with variable lead times, and because run times are variable, when running 10 eaches, it may only take a day to manufacture, but when running 10,000 eaches, several days may be needed to manufacture the item. Now, we'll review the options you have with each lead time concept. The available options for managing lead times are based on whether the item is purchased or manufactured. If the item is purchased, fixed lead time days to replenish material is always used. It is identified and entered manually for each purchased item. If the item is manufactured, the business must decide which option is best. There are 3 options that exist. Will the business manually enter a fixed lead time days value, where it's the lead time that is manually identified or determined and then manually entered for each item? Or will the business allow the system to calculate a fixed lead time days value? This is the lead time the system calculates and is based on the item's standard manufacturing routing and a standard lot size that is typically manufactured, where the routing and the manufacturing lead time quantity is manually entered for each item. The third option, will the business allow the system to calculate a variable lead time per unit value? It's the lead time the system calculates based on the item's standard manufacturing routing and displayed using a time basis code. An example of time basis code would be hours per each, or would we display our time hours by 10 eaches or hours by 100 eaches, so on and so forth. For example, hours per 1,000 each. The business must decide which option best fits their planning strategies. To decide which is best for your business, you must understand JDE's lead time concepts and backscheduling logic. In order to understand these concepts and options, we'll need an example to work with. The following graphical presentation of a multi-level bill and routing structure will be used to showcase JDE's lead time calculations and backscheduling features. Let's review it now. In this multi-level bill of material and routing structure, we will buy material and then add value to it through work centers that have operations. These operations have components of lead time that we may need to account for. There's queue time, that is the time that sets and staged in front of operation sequence. And then when we begin the sequence, there could be a certain amount of changeover or setup time before we can actually start running the job. The time could be machine paced or labor paced. So we'll need to account for either machine run hours or labor run hours as we add value to this material. Once we complete product through these operations, there could be a certain amount of move hours that we need to account for in our lead times. And then as we move this work in process from one operation to the next, or through the routing to finally finish and have a make item in inventory. In the product structure, material handling functions is shown with the green arrow, and external lead time is shown with the blue arrows. Now, I've created a time horizon where here's today, and as we move forward through the timeline, here's this week, and moving forward into the future, next week, and then into future weeks. We will build product where we buy material from suppliers, add value to it to make items that we will ship to customers. In this example, we will manufacture a finished good F611405 item number. Now, independent demand will be placed on this finished good item either in the form of sales orders or forecasts, and they'll have future dates that we are expected to make this product by. So, J.D. Edwards will use lead times to back schedule from this finished good make item back through its routing, in this case where 2 work centers will perform 3 operations, 10, 20, and 30. Now, to make this finished goods F611405, there's components that are needed and needed at certain operations. In this example, there are 2 semi-finished items that must be manufactured, and then certain other purchase components that come into the line or the routing sequence as we move the work in process from one operation to the next. Now, these semi-finished item components that are needed to make an F611405, you can assume that these are common components, manufactured components, that go into other finished good items. So if we were to do a where used inquiry on P35110, you would see that that component would go into many other finished good items. If it didn't, and this P35110 was mutually exclusive only for building F611405, then there would be no need to have this item number placed into stores on the shop floor or supermarket. We would just simply eliminate that item number and attach the previous operation that makes this and call this work in process. But in this example, these 2 manufactured components have where used functionality where they go into many other finished good items. On the shop floor, there are supermarkets where we build material to and then draw from or pick from and then stage at work centers when a work center schedule calls for this material. So when we review this product structure, you begin to see a multi-level bill of material and routing sequences with all of the lead time components that we may need to account for. For example, to manufacture a semi-finished item P36754, we need only one component. Let's call it a raw material. This raw material item must have a fixed lead time that we will use to figure out when we need to start buying or when we need to order by, so that it is delivered when we need it and when the scheduled start date of Operation 10 must occur in order to stay on time to move through this bill of material and routing structure to finally finish F611405 that we ship to customers. These purchase items that we buy from suppliers will go and be received at the receiving dock and then put away into raw material storage locations and remain there until there's a time when the work center schedule at this first work center, which lists the sequence of orders in which they should be started and done by, we will then pick and stage this material at those work centers when they near their start dates. Now, when it's sitting at the operation, there could be a certain amount of queue time we need to account for, and before the job starts. When the job is about to begin, there could be some changeover time or setup time to process or cycle through either the machine run hours that are needed to add value to this material, or in this case, it could be just a labor-intensive or labor-paced work center where we would account for and plan for its labor hours for the cycle time of this material through Operation 10. Once we've completed our first pallet or crate or basket or tub of material, and there could be a certain amount of move time that we might want to account for to take that work in process and move it or transport it and stage it in front of the next operation. Now, this work in process, again, may need to account for a certain amount of queue time at this work center for the next operation. And then that material, there could be a further setup or changeover at this operation before, in this case, we need to cycle the machine through its process to add value to the material. So we would account for its machine runtime, and then when we have a completed pallet or basket of parts or a crate, there could be a certain amount of move time that we account for to move it to its shop floor supermarket. And therefore, we now have some inventory for P36754. Again, we will need P36754, P35110, and 3 other purchase components when we go to pick this material and then stage it at its upstream work center called SABL01. Again, there will be a certain amount of queue time we may need to account for before the work center schedule says we need to start this by in order to set it up and change over and then begin its labor content of adding value to those parts and transforming it into WIP. Now, this WIP in between Operation 10 and 20 may need a certain amount of move time to get it to its next operation. If this was a line, a single piece line, then there probably wouldn't be any move, and this next operation is right next to the previous downstream operation, and then it would begin to sit in queue before the next operation is able to start it and then it has a certain amount of setup before the labor hours that are needed to transform it into a WIP that is needed at the upstream operation 30. Again, there could be some move and queue time that we may need to account for to get this WIP to operation 30. And then finally, when we finish the last operation, we will have our finished good item. The user should refer to this graphical presentation of this multi-level bill and routing structure as we move forward through examples and demonstrations of lead time calculations and back scheduling logic. Before we begin, there are some prerequisites or master files you must understand first. So let's get started with that. First, when we break the prerequisites down into prerequisite for purchase items and prerequisite for manufactured items, for purchase items, which we know will always use fixed lead time concepts, users should be aware of the branch plant constants and the values set that establish the facilities in which we will operate in. Obviously, there must be item master and item branches for all our purchased items, and all those purchased items must have manually entered fixed lead time data, and this data is stored in the item branch. Other prerequisite master files needed for make items are: the user must be familiar with the manufacturing constants. And there is a key attribute in the manufacturing constants for our facilities where we operate in called the work hours per day. And so therefore, in our example moving forward as we demonstrate lead time calculations, our sample branch plant has a manufacturing constant setting where the plant operates only one shift and one 8-hour shift. Excuse me. Furthermore, this plant must have a shop calendar indicating the work days in which the shop operates. In our example, we do not plan to work on the weekends. Therefore, the shop calendar has Saturdays and Sundays as non-work days. Now, that doesn't mean we can't run overtime if we fall behind in our schedules, but from a planning perspective, we're going to plan to shop days for manufactured items. Next, the user must be aware of each routing operations work center master. Here are some key attributes the user must understand in the work center master. First is the prime load code. The prime load code of a work center determines whether the work center is a labor-paced or machine-paced work center. And if it's a labor-paced work center, users must be aware of the number of employees assigned to that work center, or if it's a machine-paced, they must be aware of the number of machines that are running in that work center. In that work center, work centers can be efficient or inefficient and utilized or unutilized. And therefore, there's efficiency and utilization percents in these work center masters. Once we have those attributes set in the work center master, the last critical attribute in the work center is the work center's shifts of operations and hours per shifts. In this example, work centers we will look at, these two work centers are flagged to run 8.5 hours and 1 shift per day. Now, there are many work centers in a plant. Remember, our plant was just set to use 1 8-hour shift, but apparently these two work centers, in the way we have our employees set to come into work and go home after work, they will work 8.5-hour shifts, 1 shift a day. Once the work center masters are in place, users must be aware and generate resource units for each of these work centers. I like to refer to these as a work center calendar. Now, the shop, which runs 8 hours a day, has a shop calendar. But each work center with a monthly calendar can have its own work center calendar or resource units. Therefore, since this work center is an 8.5-hour 1 shift operation, you can see we are planning for 8.5 hours each day. Now, later on, we're going to learn about shop floor work orders and how they're back scheduled, and they're back scheduled using rated capacity. We'll see later where rated capacity will take these gross hours per day and then factor them by the efficiency and utilization. An example of utilization would be if this work center is scheduled to run 8.5 hours a day, we may not fully utilize all 8.5 hours. For example, when employees come to work and clock in, there might be some startup activities, maybe some preventative maintenance. There might be some team meetings to kick off the day. So if you subtract, say, 10 minutes for the beginning of the day, and then let's say at the end of the day, these employees get a 10-minute cleanup or wash up, and maybe another 5 minutes to shut down and talk to their supervisors about how their day went. There's some more time that is not utilized. So we want to subtract that time. Also, there's morning coffee breaks and afternoon breaks. When you factor or minus out that unutilized time, you begin to see a utilization percentage. Now, efficiency is how efficient we are to our routing standards. If we have a routing standard that it should take 1 hour to make 1,000 eaches, how efficient are we to that engineering standard? Are we constantly producing 1,000 pieces in less than an hour? Or are we constantly producing pieces, more pieces than an hour? So now you begin to see how efficient we are to the engineering standards. For make items, obviously all of those make items must be in the item master and item branch master, and we must have their routings entered in the routing master, along with all bill of materials for these make items must be in the system before we begin any lead time calculations. Once we have all this master data in place, we'll simply perform an integrity analysis across our bill of materials. This will check our bill of materials to make sure we have no recursive situations where a parent is made out of itself. And this usually runs nightly, and it will reset all of the low-level codes in the bill of material that make it a multi-level indented bill of material. All bill of materials have a product structure, and the low-level code sets that indented bill of material in the bill of material. Finally, we're ready to begin our lead time roll-up, which usually runs nightly automatically as engineers are making changes or adding items in bills and routings. We'll need lead times calculated for those, and the R30822A is the program that we'll learn about that calculates lead times. So as we move through and demonstrate and discover lead times, it's important to know that before you start operations in the plant, all items must have lead times. All lead time attributes are stored in the item branch master. And then finally, if we are a multi-facility environment where maybe one plant supplies material to another plant, we must make sure we understand and set up what is called the branch plant relationships master and identify the transit days between facilities. That is another component of lead times. Here is an example of a multi-facility or a multi-branch plant where one plant supplies material to another. Now, if we were to make this finished good item in a branch that's in Tennessee and we ship to customers or to a distribution center, to make that item back through its routing operations, there are two components needed. One component we buy from a vendor that has a fixed lead time that we need to account for. The other component is a purchase item that we get from the other plant. And at the other plant, they make it. So in the branch plant relationships table, we need to account for the lead time that it takes to transport it from one plant to the other. And in the branch plant relationships table, there's a transit day attribute. In this example, we are allowing for 5 days, and the transportation method is by a carrier or trucking company. Now, if these plants were, say, in a different country, let's say Tennessee and China, then this transit day value would be set to a greater days because, say, maybe it must be transported via a shipping company or a ship may have to deliver it overseas. In some cases, we might find it cheaper if this was a Tennessee company and this was a Canada company, and we chose and have negotiated the transport via rail, then it might be 7 days, for example, for the transit days in between both of these branch plants. So the transfer lead time is set using the transit day setting in the branch plant relationship. We'll first review lead time options for purchased materials. When it comes to lead time options for purchased material, there is only one option available, and that is to manually enter fixed lead times. Here is an example of the item branch master for a purchased item. Here are some tips when entering fixed lead times for purchase items. First, the fixed variable flag tells us which lead time concept we're using. For purchase items, this flag must be set to F for fixed lead times. Then we simply enter the fixed lead time to replenish this purchased item in the lead time level attribute field. In this example, P35980 will require 112 days to replenish this purchased item. Finally, for purchase items, the manufacturing lead time quantity must be set to blank when you're manually entering lead times for purchased items. We'll discuss the manufacturing lead time quantity attribute and all of the other attributes of lead time as we progress through this presentation. But for purchase items, which are always fixed, you will always manually enter the number of days to replenish the item in the lead time level field and assure that the manufacturing lead time quantity is blank. Now, when the lead time roll-up program R30822 runs, this is the program that calculates lead times for both purchased and make items. But for purchase items, the only field calculated by the system is the cumulative lead time. Basically, it will copy the lead time level and paste it in the cumulative lead time value for you. The lead time level and lead time cumulative value will always be equal to each other when items are purchased. Next, we'll review lead time options for manufactured materials. Now remember, lead times for manufactured materials can be manually entered using fixed lead time concepts or calculated by the system. If we were to manually enter a fixed lead time for a manufactured item, we would set the fixed variable flag to F, indicating we want fixed lead time concept. And again, set the manufacturing lead time quantity field to a blank, and then manually enter our fixed lead time days to replenish the manufactured item in the lead time level field. The system will then use this fixed value when we cut work orders. It will always use this fixed lead time days of 10 to manufacture the goods. An important note about the manufacturing lead time quantity. A blank value tells the system not to try and calculate the lead time days value because you are or have chosen to manually enter a fixed lead time days to replenish. If we were to want it to calculate our lead time level for using fixed lead time concepts, we would populate the manufacturing lead time quantity. But if we are to manually enter fixed lead times for a manufactured item, you would set the fixed variable flag to F, make sure the manufacturing lead time quantity is blank, and then simply enter your fixed lead time days to replenish in the lead time level field. Now, when you run the R30822 lead time roll-up program, it will calculate all the remaining lead time attributes for you. And these will become or be known as informational lead time data. Work orders would always be scheduled using the manually entered fixed lead time days to replenish when you choose to use the fixed lead time concept for make items and manually enter that fixed lead time. If we were to allow the system to calculate our lead times, we would set the fixed variable flag to either a V for variable concepts or an F for fixed concepts. In this example, we'll set it to V for variable concepts. Because we want the system to calculate our lead times, we must populate the manufacturing lead time quantity. You set this manufacturing lead time quantity attribute to a value equal to or greater than 1. It is recommended that you enter a value that is most typically ran or a standard lot size. When doing so and running the lead time roll-up program, it will calculate all our lead time attributes using formulas. There are two formulas used: a formula to calculate the lead time per unit and a formula used to calculate the lead time level when you want the system to calculate them. Again, a non-blank value tells the system you want the lead time roll-up to calculate. If this is blank, it will not calculate. All lead time attributes calculated by the system are highlighted in yellow. And all these lead time attributes are stored in the item branch. The program that calculates these is the R30822A, the lead time roll-up program. Here is an example of a purchased item using fixed lead time concepts, the only option available for purchased items, where we enter an F for fixed. We assure the manufacturing lead time quantity is blank, and we simply enter our fixed lead time days to replenish this purchase item in the lead time level field. When the lead time roll-up program runs, it will calculate for us the cumulative lead time simply by copying and pasting that value from the lead time level field into the cumulative lead time. For a manufactured item using either fixed or variable lead times, all the lead time attributes will be calculated for us, but when using fixed or variable lead times, the lead time roll-up program uses two formulas to calculate the lead time per unit and another formula to calculate the lead time level values. We'll review those formulas later. So we can summarize the system's back scheduling logic with this matrix. Again, we know that purchased items and manufactured items have a concept that you must choose to use. We know that purchased items are always a fixed lead time, and the manufacturing lead time quantity must be blank, and you simply enter the lead time level as the number of days it's required to replenish the item. The manufacturing lead time unit, the lead time per unit, does not apply for purchase items, and there is really no back scheduling logic for a purchased item when you cut a work order. You don't use work orders for purchase items, you use purchase orders to replenish items. But for make items, you can choose to either use the fixed lead time concept or variable lead time concept. If you want to be a fixed lead time concept for manufactured items, will you manually enter it, or will you allow the system to calculate the lead time level for you? If we are to manually enter a fixed lead time for a make item, we must assure the manufacturing lead time quantity is blank, and we simply enter the lead time days to replenish in the lead time level field. When we run the lead time roll-up program, it will calculate the manufacturing lead time per unit, and it will be considered as informational only data. When cutting work orders for a manufactured item using fixed lead time, it will back schedule the work order using the manually entered lead time days to replenish that is found in the lead time level field. Now, if we were to choose to use fixed lead time concepts on a make item, but have the system calculate the lead time level, again, we must assure the manufacturing lead time quantity is of a value greater than or equal to 1, and typically we would recommend it be a typical or standard lot size. And then when running the lead time roll-up program, it would calculate the lead time per unit, which would be informational only. And then again, when we cut work orders for this manufactured item using fixed lead time concepts, it would use the lead time level value that was calculated by the system. Now, if we chose to use a variable lead time concept for our make item, remembering variable means the larger the lot size, the longer it will take, and the smaller the lot size, the less time it'll take. For variable lead time concepts, again, we must make sure the manufacturing lead time quantity is a value greater than or equal to 1, or a typical lot size. And then there are 3 different formulas used to calculate the lead time level, the manufacturing lead time per unit, and then work orders. When you cut a work order, would always use the lead time per unit information for back scheduling that work order. When it comes to lead time options for purchase material, there is only one option available, and that is to manually enter fixed lead times. You will set the fixed variable flag to F and make sure the manufacturing lead time quantity is left blank, and then simply enter the fixed days to replenish this purchased item in the lead time level field. When running the lead time roll-up program, which is used to calculate lead times for both purchased and make, for purchase items, it will simply copy the lead time level value into the lead time cumulative field for you. The lead time level and the lead time cumulative value will always be equal to each other when the item is purchased. Next, we'll review lead time options for manufactured materials. Now remember, lead times for manufactured materials can be manually entered or calculated by the system. If we were to manually enter fixed lead times for a manufactured item, we would set the fixed variable flag to F. Again, make sure the manufacturing lead time quantity is blank, and then simply enter the fixed days to replenish the manufactured item in the lead time level field. It's very important that you understand that the manufacturing lead time quantity must be blank when manually entering fixed lead times. A blank value tells the system not to try and calculate the lead time level days value because you have chosen to manually enter a fixed lead time days. When you run the R3822A lead time roll-up program, it will calculate all the remaining lead time attributes, and these attributes will be informational only. If we were to allow the system to calculate our lead times for a manufactured item, we would set the fixed variable flag to either an F or a V to use fixed or variable lead time concepts. In this example, we're setting it to a V for variable. And then you must assure, if we're going to have the system calculate our lead times, we must make sure the manufacturing lead time quantity is a non-blank value. A non-blank value tells the system to calculate the lead times and then display day values for these manufacturing lead time quantity. The lead time roll-up program R3822A is the program used to calculate lead times. All the lead time attributes calculated by the system are highlighted in yellow. All lead time attributes are stored in the item branch file. Here is a purchase items item branch record using fixed lead times that were manually entered. And here's a manufactured item that can use either fixed or variable lead time concepts. In this case, it's using variable. And the manufacturing lead time quantity is populated, and in this case, for a standard run size of 1,000. When running the lead time roll-up program, it will calculate all the lead time values for us. There are formulas that are used to calculate the lead time per unit and the lead time level, and we'll review those formulas later. We can summarize the system's back scheduling logic with the following matrix. The matrix includes purchase items and manufactured items. Again, purchase items can only use one concept, and that is the fixed lead time concept, where we set the fixed variable flag to F and assure the manufacturing lead time quantity is left blank. And then we simply manually enter the fixed lead time days to replenish the purchased item in the lead time level field. Now, for manufactured items, where we can choose whether to use fixed lead time concepts or a variable lead time concept, where variable lead time concept means the more you make, the more time you'll need, and the less you make, the less time you'll need, as opposed to fixed lead time, where the days to replenish is fixed regardless of the quantity you're manufacturing. If we were to manually enter fixed lead times for a manufactured item, we would set the fixed variable flag to F, make sure the manufacturing lead time quantity field is blank, and then simply manually enter the fixed days to replenish the manufactured item in the lead time level field. When the lead time roll-up program runs, it will still calculate the lead time per unit, but that becomes informational only. When cutting work orders for this manufactured item, it will back schedule the work order to determine a start date using the manually entered lead time level value. Now, if we chose for the manufactured item using fixed lead time, if we chose the system to calculate the lead time level for us, we would use the fixed variable flag as an F, and then we would manually enter a manufacturing lead time quantity value that is equal to or greater than 1. It is recommended that that quantity be a typical or standard lot size that's most often used or ran. When running the lead time roll-up program, the system will calculate the lead time level value for us, and it will also calculate the lead time per unit value. Now, work orders, when they're cut and back scheduled to create a start date using the fixed lead time concept, will back schedule it using the value found in the lead time level field. Therefore, the lead time per unit information is informational only. Finally, if we chose to use a variable lead time concept where it always takes longer to make larger lot sizes and less time to make smaller lot sizes, we would set the manufacturing lead time quantity to a value greater than or equal to 1, and again, it's recommended that that quantity be of a typical or standard lot size. And then when we run the lead time roll-up program, it will calculate both the lead time level and lead time per unit values. There are 3 different formulas that are used when calculating the lead time level, calculating the lead time per unit, and another formula used when back scheduling work orders. When back scheduling a work order to determine its start date, for variable lead times, it will use the lead time per unit value. We'll cover these formulas later. When it comes to lead time options for purchase material, there is only one option available. That is to manually enter fixed lead times. For a purchase item using fixed lead time concepts, we'll set the fixed variable concept flag to an F, and then assure the manufacturing lead time quantity value is blank. And then we'll simply enter the fixed lead time days to replenish the purchased item in the lead time level field. When we run the R3822A lead time roll-up program, which is used to calculate lead times for both purchased and manufactured items, for purchase items, it'll simply copy the fixed lead time level days value into the cumulative lead time attribute field. The lead time level and cumulative lead time value will always be equal to each other when the item is purchased. Next, we'll review lead time options for manufactured materials. Remember, lead times for manufactured materials can be manually entered or calculated by the system. If we were to manually enter fixed lead times for manufactured items, we would set the fixed variable flag to F, make sure the manufacturing lead time quantity is blank, and then simply enter the fixed lead time days to replenish the make item in the lead time level field. It's very important to understand a blank value in the manufacturing lead time quantity field tells the system not to try and calculate the lead time level field because we've manually entered a value there. If we were to mistakenly enter a quantity in the manufacturing lead time quantity, and when running the lead time roll-up program, it would replace our manually entered value with a calculated value. So when we want to manually enter fixed lead times for make items, enter an F, always make sure the manufacturing lead time quantity is blank, and then manually enter your fixed lead time days to replenish in the lead time level field. When you run the R3822A lead time roll-up program, it will calculate all the remaining other lead time attribute fields. If we were to allow the system to calculate our lead times, we would set the fixed variable flag to either a fixed F or V variable. In this example, we're setting it to a V to use variable concept. When having the system calculate all our lead time attributes, we want to assure the manufacturing lead time quantity is of a non-blank value. A non-blank value tells the system to calculate the lead times and then display those lead time day values using the manufacturing lead time quantity. In this example, to manufacture 1,000, a standard lot size of 1,000, it will take 10 days. However, 19 days will be needed to manufacture all of the manufactured items in this bill of material. And then when you include the purchased material also needed, the cumulative lead time is now 126 days to manufacture this manufactured item. The lead time roll-up program, R3822A, is the program that calculates our lead times. All lead time attributes calculated by the system are highlighted in yellow, and these lead time attributes are always stored in the item branch file. Again, I've placed a purchased item right next to a manufactured item. For purchase items, we only have one option, and that is to use fixed lead time. In summary, we would set the fixed variable flag to F, assure that the manufacturing lead time quantity is blank, telling the system not to try and calculate anything, and then manually enter the fixed lead time to replenish the purchase item in the lead time level field. When the lead time roll-up program runs, it will copy and then paste the lead time level value into the cumulative lead time for us. For a manufactured item, using either fixed or variable lead time concepts, in this example, the item's fixed variable flag is set to use variable lead time concepts, where the more you make, the more time you'll need, and the less you make, the less time you'll need. When setting the system to calculate our lead times for us, we must remember to set the manufacturing lead time quantity to a non-blank value. It is recommended that we set the manufacturing lead time quantity to a typical run size or a standard lot. In this example, when running the lead time roll-up program, there are two formulas used to calculate the lead time per unit value and the lead time level. We'll cover those formulas later. We can summarize the system. We can summarize the system's back scheduling logic with this matrix. Remember, purchase items always use the fixed lead time concept, where we set the fixed variable flag to F, and we always make sure the manufacturing lead time quantity value is blank. Then we just simply enter the number of days it takes to replenish the item in the lead time level field. For manufactured items, where we have a choice to use fixed or variable lead time concepts, for fixed lead time concepts, you must determine whether you'll manually enter the fixed lead time to replenish the make item, or if we want the system to calculate that for us. If we were to manually enter a fixed lead time to replenish the item, we would set the fixed variable flag to F and make sure the manufacturing lead time quantity is blank. Then we just simply enter the number of days it takes to replenish this fixed lead time manufactured item. Now, when we run the lead time roll-up program, it will calculate the lead time per unit for us, but that is simply informational only data. When we cut work orders for a manufactured item using fixed lead times that we've manually entered, it will back schedule the work order and create a start date using the lead time level value. But if we were to have the system calculate our fixed lead time level value, we would set the make item to an F, make sure the manufacturing lead time quantity has a value greater than or equal to 1, or it is recommended that it be a typical run size or a standard lot size. Then, when running the lead time roll-up program, it will calculate our lead time level to manufacture that item, and will calculate the lead time per unit value. The lead time per unit value, again, would be informational only, and when cutting work orders, to determine a start date of that work order, it would back schedule it using the lead time level value. If we chose to have a manufactured item using variable lead time concepts, we would set the fixed variable flag to V and again enter a typical run size or standard lot size in the manufacturing lead time quantity field. Then we would run the R30-822A lead time roll-up program, and it would calculate both the lead time level and the lead time per unit fields. When we cut a work order for a manufactured item using variable lead time, where it always takes longer times to make larger lot sizes and less time to make smaller lot sizes, when we cut the work order, it would back schedule using a formula that taps into the lead time per unit value. Now, there's 3 formulas used to calculate the lead time level, the lead time per unit, and another formula used to back schedule work orders. We're going to cover each of those formulas in detail later on in this workshop. I mentioned earlier that all lead time attributes are stored in the item branch master. However, JDE also provides a lead time inquiry. It is a multi-level bill of material showing the lead times for all components needed to manufacture the parent item, and it shows all its lead times for those components. Here's an example of the lead time inquiry, where a finished good item F611405 is showing all of the components needed to manufacture this item. It's a multi-level indented bill of material. But let's first understand the purchase materials. All the purchase materials are highlighted in yellow. This multi-level bill of material for a manufactured item displays all components needed. These purchase materials highlighted in yellow are showing all of their level lead time values. For example, to make an F611405, there is a purchase component P35980 that is needed to manufacture P35110. That manufactured component goes into the F611405. We were just looking at this P35980 purchased item where we were manually entering a fixed lead time days to replenish of 112 days. The lead time roll-up program copied that 112 days to the lead time cumulative value. In the lead time inquiry program, you can see the lead time level and cumulative lead time values are shown for each of the purchased components. Next, we'll review lead time options for manufactured items. Just like purchase items, these lead time attributes for manufactured items are stored in the item branch master. When it comes to lead time options for manufactured items, if the item is manufactured, the business must decide which option is best. And an item can use one of the following three options. They can be fixed lead times, where we either manually enter them or allow the system to calculate them. Or we can choose to use the variable lead time concept that the system will calculate for us. Now note, calculated lead times depend on and rely on the integrity and accuracy of the item's standard manufacturing routing data. Now, companies that do not have item routings or have outdated or incompleted routings or just integrity or accuracy issues with their routings may consider using fixed lead times that are manually entered. Now, companies that have a high degree of routing data integrity and accuracy, where lot sizes or manufacturing run sizes or batch quantities are consistently the same value from one work order to the next, let's say in a make-to-stock environment, they may consider the use of all three options. They may consider using fixed lead times that are manually entered, or they may consider using fixed lead times that are system calculated. Or they may even consider using the variable lead time concept that the system calculates for us. Now, companies with a high degree of routing data integrity and accuracy, where lot sizes or the manufacturing run sizes or batch quantities vary from one work order to the next, let's say in a make-to-order environment, probably are going to consider using the variable lead time concept that the system will calculate for us. The most popular lead time option used, I gotta say, as a consultant of J.D. Edwards, is variable lead times, where the more you make, the more time you'll need or allow for the manufacturing process. This is compared to using fixed lead times, where the quantity manufactured will always use the same fixed number of lead time days. For example, for fixed lead times, to manufacture 10 pieces, you allow 5 days to complete the order, and to manufacture 10,000 pieces, you allow the same 5 days to complete the order. We'll start with reviewing variable lead times first, and then later on and at the end, we'll review fixed lead times. But first, we must review each lead time attribute field and learn what each value means and does. And then finally, how the system uses these values to perform back scheduling logic. There will be a quiz at the end, so study each value carefully. I have presented the item branch master along with the lead time inquiry for our manufactured item F611405. The R3822 lead time roll-up program is the program used to calculate all these lead time attributes. We'll cover each lead time attribute highlighted in yellow, but first let's discuss the fixed variable flag attribute and how this item branch master form relates to the lead time inquiry form. Remember, the fixed variable attribute field tells the system whether the item should use fixed or variable lead time concepts. We're discussing the variable lead time concept first, and then later on we'll discuss fixed lead times. You will note that the attributes lead time level, lead time manufacturing, and lead time quantity, or cumulative, are also shown in the lead time inquiry for our item. Next, we'll review the lead time manufacturing quantity. Again, this is the attribute that tells the system whether lead time should be calculated or not. When blank, the system will not attempt to calculate lead times. It uses the manually entered lead times. But when the value is greater than or equal to 1, the system will calculate lead time. When manually entering fixed lead times, this value must be blank. When allowing the system to calculate lead times, this value cannot be blank. Again, J.D. Edwards recommends that the manufacturing lead time quantity be set to a value the shop is most likely to manufacture. Let's say a typical lot size or standard run quantity. All of these lead time values here, for example, 10 days, 19 days, and 126 days, those values are displayed for the quantity that is set in the manufacturing lead time quantity. Next, we'll review the lead time level, lead time manufacturing, and lead time cumulative attributes. Again, there's going to be a quiz at the end, so study each carefully. When it comes to the lead time attributes for a manufactured item, At this point in the workshop, the first question everyone asks is, what do these values really mean? Remembering how important it is to note that the values shown are always the values for the quantity in the manufacturing lead time quantity field. The lead time level field is the number of days to manufacture this item only and only at this level in the bill of material. It is the number of days needed to manufacture this item and the quantity shown in the manufacturing lead time quantity field, and when all the components needed to manufacture this item are on hand and available. Now, the lead time manufacturing attribute, it is the number of manufacturing days needed to make the item through the entire bill of material and for the quantity shown in the manufacturing lead time quantity field. It's the number of days needed to manufacture all of its lower level assemblies on the item manufacturing critical path, and when all purchased components needed are on hand and available. Where the lead time cumulative is the total number of manufacturing and purchasing lead times along the critical path in the bill of material and for the quantity shown in the manufacturing lead time quantity. It is the number of days needed when no material is on hand or available, or when everything must be purchased and manufactured to make this item. Let's review and understand this critical path of a manufactured item. First, let's assume we have no material on hand and the manufactured item has to be made from scratch. All the material we need to manufacture this item must be purchased and made. Therefore, the critical path would be the longest path through the bill of material and its cumulative lead time days to replenish it. So, going back to our multi-level bill of material product structure and routing operations, visually, you can kind of see from this indented bill of material, you can kind of get a flavor of what the critical path could be to make an F611-405 going backwards through the bill of material and its routing sequences. A critical path could be this path here. But we won't know that for sure until we look at the lead times for each of the purchased items and the make items. It just could be the critical path to make a 611-405 could be this path. The critical path is important because that's the path that we must be perfect on if we are to hit all of our promised and scheduled dates, where items not on the critical path have a little leadway. When understanding the critical path for a manufactured item, how does a user recognize this critical path for a manufactured item? Well, within the lead time inquiry program, and looking at it, you can pick out the paths. In this scenario, there are 4 paths involved to make item F611-405 that requires 10 days to manufacture 1,000 eaches. The first path I see is from a multi-level bill of material, indented bill of material. The components needed at level 1, I can see a purchased path. purchased items in level 1, what is the longest lead time? I see the longest lead time as 35 days. If 35 days to purchase this item plus another 10 days to make this item, that path is 45 days. When looking down level 1 components needed, I do see a phantom involved, a pseudo item that engineers use to help structure bills of materials. This phantom item calls a purchase item that is 28 days to replenish. So in this path, the lead time of 28 days plus the 10 days to make the 405, that's 38 days. Well, path 1 is still longer. However, I do recognize 2 manufactured paths. Here's a path where this make item needs this purchase item. And this make item is needed to make the F611-405. When I look at the lead times for this path, 30 days plus the 9 days plus the 10 days gives me 49 days on that path. When I look at the other manufacturing path to make a P35110 that requires this purchased item, to procure that purchased item, our suppliers require 112 days of lead time to replenish it. When adding that to the 4 days to make this semi-finished item and the 10 days to make this item, that is 126 days. Therefore, my critical path is path 3 to make an F611-405. I need this semi-finished item P3510 that needs this purchased item. My cumulative lead time days is 126, and this is the critical path. Now, there is a common complaint about the lead time inquiry form. When looking at the lead time inquiry, in this example F611-405, we can see the level, the manufacturing, and cumulative lead times that are stored in the item branch master, also on the lead time inquiry. There's a complaint that users are always constantly asking, why isn't the manufacturing lead time quantity also displayed on this form? Users are constantly complaining that they have to drill into the item branch just to see the manufacturing lead time quantity. Then they know or have meaning to what these day values mean. For example, it takes 10 days at this level to make an F611-405, and that is for 1,000 eaches. Well, there's 2 solutions for this complaint. One is to set up a Cafe 1 page to view the manufacturing lead time quantity quickly. And number 2, it's recommended to establish a rule-based standard the company will use for the manufacturing lead time quantities. However, it's not uncommon for businesses to make a standard rule for the manufacturing lead time quantity values and what they should be for all manufactured items, and also make a Cafe 1 composed page. Having a standard rule means when users access the lead time inquiry form, they know the lead time days values are always for a standard quantity. Therefore, eliminating the need to always drill into the item branch master and find this manufacturing lead time quantity. The remaining presentation assumes a rule that all manufactured items will use a manufacturing lead time quantity value of 1,000. I'll explain this rule further on the next slide. But before I explain the rule and why it's recommended, here's an example of the lead time inquiry form where the user has customized their screen to add a hotkey or a hot button that will take them directly to the item's item branch master and show them the manufacturing lead time quantity. So after the user types in F611405 and clicks Find, and they're viewing the level lead time and the manufacturing lead time and the cumulative lead time, and they want to know, well, what's these days values for? What's the quantity size that they're based on? They can click this button and the screen will then split into two applications. I quickly can see that it takes 10 days to manufacture 1,000. So setting up a Cafe 1 user-defined object is always helpful. But it doesn't stop there. You can see this user not only added a Cafe 1 page for the item branch, but they've also added a button so that they can reference the routing quickly. If you have a large LCD display, say a 21-inch, these screens really look nice on your desktop. But let's look at why it's best to have a rule for the manufacturing lead time quantity. Again, with our composed page, when using the lead time inquiry, and it takes 10 days to make 1,000 F611405s, but for part number F611405, if the value was 1 day, I would see, oh, that is for a quantity of 1. So the composed page is very valuable when you're looking at an item. These days values are for 1,000, but if the manufacturing quantity was 1 and I were seeing values like this, clicking on my composed hotkey shows me it takes 1 day to make 1 each. Takes 10 days to make 1,000. But let's take a look at why it's best to have a rule for the manufacturing lead time quantity. Some rules that work well that I'd like to recommend leverage this time basis code value. You see, the time basis code sets the item precision level for specifying run times in the item routing file. The value you set here, in this case, hours per 1,000, will default into the routing when engineers are adding an item routing. Time basis code 3, hours per 1,000 units, indicates the engineer should be entering run times for 1,000 units. Now, the reason a time basis code is needed in JD Edwards is that the routing runtimes will only support 2 decimals. The time basis code is required when 2 decimal places are not enough for entering runtimes at an accurate level. For example, if an engineer needed to enter 0.05055 hours per each, J.D. Edwards will round this to 0.05, which is less accurate. Therefore, by leveraging this time basis code, hours per thousand, we can maintain a higher level of accuracy and then enter, in this example, 50.55 per thousand eaches. We're basically moving the decimal 3 places. That gives us the accuracy we need. Now, it's real common for companies to create a rule for the time basis code. The time basis code rule for all manufactured items and uses the time basis code. So if you choose to set your routings at a time basis code of hours per thousand, it is best or recommended that you use the same quantity for your manufacturing lead time quantity. Now, whenever users are looking at routing, they know, hey, it's hours per thousand. Whenever users are looking at lead time data, they know it's days per thousand. This rule works well, and users quickly become used to this, and it's second nature to them when viewing routing times. Oh, it's always hours per thousand. And when viewing days, lead time days, they know it's always days per thousand. That's a rule that works well. Next, we'll learn about the lead time per unit attribute, what it means, what it's used for, and when an item is using these variable lead times. Remember, the R3822 lead time roll-up program will calculate a manufactured item's lead times. The lead time per unit is the hours per unit and is always displayed at or using the time basis code. In our example, hours per thousand units. It takes 80.55 hours to make 1,000 units. Now remember, the system will only calculate the lead times when the fixed variable flag is set to a V or F and the manufacturing lead time quantity is not blank. Again, J.D. Edwards recommends the manufacturing lead time quantity be a value equal to a standard lot size or a typical run size for the item. However, it is not uncommon for businesses to make a standard rule for what the manufacturing lead time quantity should be. In this case, the company decided to leverage their rule based on setting the time basis code to always use hours per thousand units. Therefore, their rule for the manufacturing lead time quantity was to use the same 1,000. Therefore, the lead time days value are always displayed for this 1,000 pieces, and the lead time per unit is always displayed at 1,000 eaches, equal to the time basis code. Now, the manufacturing lead time quantity allows the system to calculate the lead time level field. When it's populated, it calculates. When it's not populated, it won't calculate the lead time level field. It's expected that we'll manually enter them. But the lead time per unit field is always calculated. And there's a formula that is used to calculate it. We're going to be reviewing that formula. But in summary, the lead time per unit is the number of hours needed to cycle through all the routing operations to make the item. It's the value added only operational time. In our example, again, it's 80.55 hours per 1,000 eaches. Our run times in our routing were entered at a time basis code of 3 hours per 1,000 units. Therefore, the sum of our value added time through all operations is calculated and displayed in the lead time per unit field. In our example, 80.55 hours per 1,000. To understand its calculation of how it calculates the lead time per unit, we must know or be aware of some details about each operations work center. I've displayed the work center master for some of the work centers on our example product structure and routing structure. For manufacturing an F611405, these two work centers are used. Both work centers are labor-paced, where only one employee is assigned to the work center. Therefore, if there's 8.5 hours per shift, and only one employee, basically our resource units are 8.5 hours per workday. If there were two employees assigned, it would be 8.5 hours times 2 to give us our 17 hours per day gross capacity. And then finally, both work centers that are labor-paced are using 100% efficiency to our engineering standards set by engineers. Being aware of this data helps us understand when using variable lead time concepts, the work order routing start dates are back scheduled using the routing's planned hours and the work center's rated capacity. So again, here is the gross capacity for our work center called ASSE0F, where the work center was working labor-paced with one employee at 8 hours, 0.50. Again, if there were two employees assigned to this and that work center operates 8.5 hours, our gross capacity would have been 8.5 times 2, or 17 hours per day. But in our example, there's only one employee assigned. When the work order routing is attached to a work order and it begins to back schedule and create start dates, when using the variable lead time concept, it will back schedule using rated capacity hours available. These rated capacity hours are a factor of the gross capacity factored by efficiency and utilization. Now, if efficiency is 100% and utilization is 90%, then our factored percent is 90%. It's not totally utilized, but we feel that the process is 100% efficient to what the standards have been set to. So 1 times 0.9 is 90. When I take the 8.5 hours per day factored by the efficiency and utilization factor, we can only expect to produce 7.65 hours of work through the work center each day. Again, the work order routing, when using variable lead time and when it's back scheduling the planned amount of hours, it will back schedule using rated capacity. Let's review the formula used to calculate the lead time per unit. Now that we've looked at the work centers, let's look at the formula for lead time per unit. Here it is. First, it's a sum of all the routing operations. And in the legend, where M or L is going to be the machine or labor run hours based on the work center's prime load code. Our prime load code in our example for the SABLO1 and ASSEOF was prime load code labor pace. Therefore, we're going to grab the labor hours in this formula, not the machine hours. This is a labor pace. The time basis code from the item branch is used in the formula as well as the time basis code in the routing. Here's the time basis code from the item branch and the time basis code. Remember, our rule was to always set our routing run times at hours per thousand eaches, and to leverage that and also use the same 1,000 in the manufacturing lead time quantity as a company rule. The number of employees and number of machines is used in the formula. So if it was labor hours or labor paced, it'd be labor hours divided by number of employees. Where if it was machine paced, it would be the machine hours divided by the number of machines. Efficiency and utilization percentages are used in the formula, as well as the cumulative yield in the operations routing. In our example, the engineers, through their times observations and studies, says that this operations yield is 100%. You can notice there's no setup time in this. There's no machines involved. It's all labor paced. And these employees accrue a size of 1 when they're manufacturing this a work order that takes 50 hours, 0.55 per thousand. They're not expecting to spoil, or they're not anticipating any scrap because the cumulative yield is 100%. So there's the formula, and if I work the formula, let's see if we can get to 80.55 hours per thousand. For operation 10, which is a labor paced and had an employee of 1, I would take the labor hours, 50.55, divided by the number of employees, which was 1. Then we're going to divide that by the efficiency and utilization, or by efficiency, because the formula, if it's labor paced, will use efficiency. So our efficiency was 1, or 100%. Then times the cumulative yield, which was 100%. We're going to take all that and multiply it by the time basis code, which is 1,000 from the item branch, and then divide that by 1,000 that we find in the item routing. That gives me 50.55 hours per thousand for the first operation. When I sum the calculation for operation 20, where it takes 15 labor hours divided by the number of employees in that work center, take that divided by the efficiency of 100% times the yield of 100% multiplied by the time basis code in the item branch, all divided by the time basis code in the routing, I get 15 hours per 1,000 eaches. Finally, doing the same thing again for the third operation, the sum of all three of these calculations is 80.55 hours per 1,000. So there you have it. There's the formula for lead time per unit. So there's always some questions that come up after the users, that is, see this formula for the first time. And they ask, hey, why isn't setup in queue in move hours a part of the lead time per unit field? Here's another item in our bill of material. Remember the semi-finished unit that goes into the finished good unit, P36754, has a labor-paced work center with employee 1 in it and a machine-paced work center that has only 1 machine in it. Again, the lead time per unit is only the operational cycle time of the run machine or labor run times in the routing. It does not include any queue or move hours. We'll see later when we get to work orders in the formula used to back schedule work orders, where it takes into account this lead time per unit, it will add in the setup hours and any queue and move hours, because you see those are fixed hours. It doesn't matter whether I'm making 5 pieces or 5,000 pieces, the setup time is static or fixed, as well as it doesn't matter whether I have a tub of 1 or 3 tubs. The queue and move hours are always fixed. So later on, when we investigate the formula used to back schedule work orders, where the lead time per unit is factored in to that calculation, you'll see how these numbers, setup, queue, and move, are added. But again, when working the formula, the first operation, which is labor-paced, 50 hours divided by 1 employee, take that divided by the efficiency of 1,000 times the yield times the time basis code in the item branch, all divided by the time basis code in the routing, I get 50 hours. However, the next work center, machine paced, where it takes 20 hours per 1,000, divided by the number of machines that are in and exist in that work center, which was only 1, take that divided by utilization, right? When it's machine divided by number of machines, then we go to divide that by the utilization percent, which we found in our work center master at 0.90 or 90%, times the yield, which was 1,000 or 100%. Times that by the hours per 1,000 in the item master, in hours per 1,000 time basis code in the item branch, I get 50 for the first operation and 22.22 hours That's because we don't utilize that machine. There's breaks, there's morning startup and end of day shutdown. It's not completely utilized. Therefore, we're going to factor that in, and it will take 22.2 hours per thousand. When adding that together, the sum of completing Ops 10 and then the sum of Operation 20, we get 72.22 hours per 1,000. So there you have it. There's the formula for calculating the cycle times or the run times in the routing that get you to a lead time per unit. This routing, step 1, 2, and 3, gave us 80 hours, 0.55 per 1,000. And then for this semi-finished manufactured item, the lead time per unit was calculated to 72.22 hours per 1,000. You can see our cycle time is a little bit quicker. We can process more or the same 1,000 pieces a bit quicker than we can at the next level in the bill of material. Now, I gotta say, all the lead time attributes are stored in the item branch, and you can view these using the P41026 item branch application. However, I gotta say, there's one additional attribute, lead time attribute, that is calculated and stored in the item branch file, but you cannot view it from the screen or the application. And that is called the lead time per unit days. Now, we just went over the calculation for the lead time per unit for our make item F611405, which was 80.55, and our semi-finished item that goes into that, its lead time per unit was 72.22 hours per 1,000. The lead time per unit days, where it's going to take these lead time units and convert them into how many days it takes to make that 1,000. Remember, our time basis code was 1,000? And to make 1,000, that's 80.55 hours. Well, how many days is that 1,000? So the lead time roll-up program, as it's calculating the lead time per unit, it's also calculating the lead time per unit days. For example, it takes 9.4764706 days to make 1,000 eaches. And the formula, as it's running through, it's a sum of each operation. There's the 50.55 hours for Ops 10. It now will take that and divide it by the work center's hours per shift, which was 8.5. So 50.55 divided by 8.5, that's 5.9470582 days per 1,000. Well, then we got to go to the next operation. 15 hours divided by the work center's work hours per day, which was 8.5. There another day and 3/4 is needed, and another day and 3/4 is needed at the last operation. When converting the lead time per unit to a day's value, the sum of all those equals the 9.4764706 days per 1,000 units. Now, remember what the system calculated? It calculated 10. There's no decimal precision on days, so therefore it will always round up. So the lead time roll-up program calculated using the formula that it takes 80.55 hours per 1,000, and that equates to 10 days to make that 1,000 lead time level. $72.22 hours on the next item was calculated to make 1,000, and that equated out to taking the 50 hours divided by the work center's shifts of operations of 8.5, and then the next operation 22.22 divided 8 by 8.5 work center shifts hours per shift. Adding those two together, we get 8.4967320 days per 1,000 unit. When rounding up, we get a lead time level of 9. So that's kind of how the lead time per unit and the lead time level are calculated, and that calculation value, so it can round, is stored in the file. And again, you can't see this on the screen. It's hidden in the item branch file. We're going to learn later that this field here, lead time per unit days, is used in the work order formula when it's calculating start dates of a work order. Now let's review the formula used to calculate the lead time level. Remember how we just walked through and got to the calculated 10 for our item F611405? It takes 10 days to manufacture 1,000. When we run the lead time roll-up program, there's a critical processing option, and it's typically set to a blank value, and that is how we're going to calculate queue and move into our lead time level field. And that setting is set to use the work center hours. So queue and move hours needs to be calculated into a day's value. And this processing option here says don't use the manufacturing constants, but go to each individual's work center master to get that. So when we work the lead time level formula, we already covered the lead time per unit formula, and with that processing option, the lead time level formula is basically the same, but includes two more new attributes. One is those work days from the manufacturing constants and the manufacturing lead time quantity. And then it's adding in the setup and total queue and move hours. This processing option where it says don't use the manufacturing constants per day, but use the work center's hours per shift, means that when this processing option's blank, this is the formula used for lead time level. If we were to put a 1 here to use the manufacturing constants, it doesn't have to adjust the formula. It just adds it in and then divides everything by the manufacturing constants. This is the most popular formula required or requested by companies. Therefore, this processing option is most likely set to blank. Let's work the formula for the lead time level field. I've done that in the math. Here would be if the processing option is set to 1. where we're just going to use the manufacturing constants. Our processing option was set to blank, where we're going to take and factor the Q and move hours by the work center shift. Now, if you remember, the branch was set to 8 hours, but each work center was set to 8.5. So when taking the formula and then adding in setup, which was 0, and the Q and move hours divided by the work center shifts, I get day calculations. Again, when I add these up, I get 10.245205, which rounds down to 10 days. A little bit confusing, but study this, work the formulas, you'll come up with the same math. So, in summary, when running the lead time roll-up, we got a lead time per unit of 80.55 hours per thousand, or 10 days per 1,000. All using the time basis code of 3, which was a rule to always be hours per 1,000, and that was leveraged to create a rule that we always display our lead time level at the same time basis value, which was 1,000. Our semi-finished unit calculated out to 72.22 hours per 1,000, or 9 days. We can process this semi-finished unit in 1,000 of them a little bit quicker than we can the finished good. Now, let's review how work orders are back scheduled using these calculated lead times. When it comes to reviewing work orders using the variable lead time concept, I've entered 3 work orders for our F611405, all for various quantities, because remember, the variable lead time concept says when a work order is due, it always takes more time to complete for larger lot sizes and less time to complete for smaller lot sizes. So therefore, if I have 3 work orders for the same item, all due on the same date, but vary where the quantity gets smaller and smaller, you can see the work order calculates or is back scheduled using a formula to determine when the item should start on or before, so that it is on time and we have our required lead time. Now, there's a processing option on the interchange work order application. Just like in the lead time roll-up program processing option, it wants to know how you want to consider Q and move hours and convert that into days. It is best practice to set this processing option to the same value we did on the lead time roll-up, and that was to back schedule Q and move hours as a percentage of work hours per day on the work center. So this is blank. It's going to use the resource units. So, summarizing work order 1 for 1,000, it came up with a start date of 10 days. I need to start on February 15th, on or before that date, and 5 days or 10 days later, I would have my item completed by the beginning of the workday on the 1st. However, for a quantity of 500, it back scheduled 5 days. If it was due on 1, go back 5 days. I would have to start on or before, no later than Friday, February 22nd to complete 500. However, I don't need to start until February 26 if the order is at 250. It calculated that you need 3 days time to make 250. So it's important to note that the system always assumes that the product needs to be finished by the very start of the day it's due. So if it's due on the 1st, it's going to make sure it back schedules so it's completed at the end of the day prior so that it's available at the beginning of the day it's due. So here's the formula used to calculate the start date on a work order header. The formula is pretty simple. The formula will calculate the number of days needed to manufacture and then back schedule those days using resource units for the work center. I call that a work center calendar, not a shop calendar. The formula is, when calculating how many days are needed or work order days, it's basically the lead time in days plus the queue and move hours converted to days, and then setup hours converted to days. So what's my lead time days, queue and move days, plus setup days? That's the number of days I need to back schedule to create a start date. So here are the components of the formula, where UORG is the work order quantity that needs to be manufactured. LTCV is the lead time conversion factor, or the lead time days value we just discussed, that is stored in the 4102 file. The time basis code from the item branch, queue and move hours, and the lead time per unit hours, and then setup hours. To calculate lead time days, it's the work order quantity times the lead time per hour days. In our example, for the work order for 1,000, the quantity ordered was 1,000, and the lead time per days was 9.47647006, divided by the time basis code in the item branch. So I get a lead time days of 9.47647006. Now I need to calculate the queue and move hours that need to be considered when making this 1,000. There was 1.5 total queue and move hours. I want to divide that by the lead time per unit divided by the lead time per unit days to get the number of days that queue and move consumes. So it takes 0.17 of a day for 1.5 hours. Then setup hours, which was 0, is always divided by the manufacturing constant's work hours per day. So adding up all of these, I get it takes 9.6464706 days to make 1,000. Round up, that's 10 days. Where when I cut a work order for 500 due on the same day, March 1st, I got to figure the lead time days. 500 times the lead time per unit days divided by the time basis code. That gets me 4.73 hours. The same queue and move total hours of 1.5 is divided by this factor of the lead time per unit divided by the lead time per unit days. That converts those hours into days. For setup, there was no setup hours in the routing for these labor-paced work centers. So adding up the lead time days, queue and move days, and setup days gets me 4.9082353, or when rounding up 5 days. If it's due on the 1st, count back 5 days. 1, 2, 3, 4, 5. This would be shop days on the work order header. I now have a start date that we can plan to. Now, the work order routing start date and request dates works a little bit different. We were looking at a work order that had calculated the start dates, but that was when the work order was just a header telling us exactly what item, what quantity, and by what date we needed the product by. The next status is to attach the work order's routing to the work order. And when it did that, and it back schedules and creates start dates for each routing, there's no real formula used for calculating the start dates on the routing. That just happens by back scheduling these hours through the rated capacity available at that work center. And when it did that, it recognized an imbalance. And when I attached the routing, it flashed a work order flash message called work order scheduling. That is warning the planner that the start date of the first operation in the routing does not equal the header start date. Remember, when we first cut a work order, all we know is we need an item, a quantity, and we need it by this date. And so it uses the lead time formula that we just discussed to figure out how many days that order takes. But eventually, after we attach a routing, or manually enter a routing in times, or maybe put in an alternate routing, and instead of running it through SAP LO1, we route it through another work center that has different times. When it attaches that in back schedules, there is a possibility that the start date at the first operation may not equal what was originally calculated. And that's when you get the flash message. So back scheduling using variable lead time concept is going to find our rated capacity and then back schedule those hours using those rated capacity, not the gross. JDE suggests that the planner, when this happens, when we see a flash message, JDE suggests the planner change this work order header start date to match the start date that was calculated for the actual routing that was attached. The request date at the last operation in the routing will always be the day before the request date of the work order header. we wanted 1,000 completed by March 1st. JD Edwards will always load the request date for the last operation for the day before, assuming that at the very end of the day on the 28th, the product will be available to complete on the very first thing on the 1st. JD Edwards assumes all the product must be done by the end of the day before, so that the material is available at the beginning of the day it's due. And then it's going to back schedule from this date and calculate a start date for this operation, and then work backwards. Here's the request date, calculate a start date. Here's a request date, calculate a start date, using a work center calendar or resource units. So how does that work out? Well, it's a little bit excessive or unreasonable to expect a planner to manually go in and change the routing dates to equal the start date on the header, or change the header date to match the routing. It's pretty common to create a custom UBE that will synchronize these dates and then eliminate the flash message. Here's a before picture of when we entered the work order. It calculated 2/15 as a start date for due on 3/1, and then when we attached the routing, we got a flash message that said, hey, warning, the start date of this header does not match the start date at the first operation in the routing. Simply by clicking this, it automatically synchronized those dates so that the start date on the header and the start date of the first operation are in sync. And it removes the flash message after that synchronization. Pretty neat custom UBE that is pretty common to be used in projects I work on. Let's now look at how JD Edwards back schedules these routing operations when using variable lead time concepts. Now, we know we got a work order for 1,000 due with a request date of 3/1, and it back scheduled it to be 2/15, 10 days. After we attached the actual routing to it, it takes always the 3/1 due date. It always loads the day before at the very last operations request date, and then works backward. It'll work backwards using not gross capacity, but the rated capacity that the work center is set up to realize. So when using variable lead time concepts, the work order start dates are back scheduled using the planned hours on the routing and the work center's rated capacity. When I do that and start backwards at operation 30, due on 2/28, here's operation 30, 2/28. By the 28th, this work center needs to produce 15 hours of work by the 28th. And when there's only 7.65 hours of capacity available, 15 minus 7.65, there's 7.33 hours remaining. Moving backwards, that means I can start the job on the 27th and produce the 15 hours required by the 28th at the end of the day. Working backwards to operation 20, I need to have operation 20 completed by the end of the day, the 26th, so that I need to start it on the 25th. Again, it was 15 hours minus the 7.65 rated capacity. That's 7.3 hours. 7.3 hours can be done on the previous day. So at Ops 20, I need to start on the 25th and have it completed on the 26th, so that on the 27th, I can begin Operation 30 and have it completed by the 28th at the end of the day, so that on the 1st of March, I will have this work order completed. It is due by 3/1. Working backwards to Ops 10, it requires 50 hours to be produced by the 22nd, because notice there's a weekend involved. So I need to complete Ops 10 no later than the 22nd, because we're shut down over the weekend, so that when I start up on the 25th, Monday, I can complete 7.65 worth of goods that will allow me to finish. When working backwards for Ops 10, its rated capacity, again, this was 7.23 rated capacity hours. 50.55 minus 722 equals 43. 43 minus is 36 remaining, and you can see how the back scheduling works for the routing, meaning that I need to start this job by the 13th of February, have Ops 10 completed by the 22nd, so that Ops 20 can start on Monday the 25th and be finished the following day, the 26th, so that the last operation can start on the 27th and then be completed on the 28th, so that by the very first thing on the 1st of March, my work order is completed. We're now towards the end of this workshop, but as promised, I said we would review how manufactured items look and behave when using fixed lead times. So let's now look at how J.D. Edwards back schedules when using fixed lead time concepts. Here's our item that has been set to variable for our previous discussions, but now has been set to use the fixed lead time concept. The lead time roll-up program calculated a lead time level for 10 days to manufacture, and that is regardless of the quantity being ordered. I cut 3 new work orders, just like we did for variable. When we were analyzing variable lead times, we looked at work orders for 1,000, 500, and 250, all due on the same date. For work orders using fixed lead time concepts, all due on the same date, you can notice that regardless of the quantity, the same 10-day period is allowed for manufacture. All work orders, regardless of the quantity ordered, are back scheduled using the same 10 days. Again, the business must figure out which is better for their environment using variable lead times or fixed lead times. And again, the most popular lead time concept used is variable. But to take this fixed lead time analysis further, when we first cut a work order at status 10, the work order start date is back scheduled by the 10 days. It takes the April 26 due date and simply back schedules 10 shop days to calculate the start date of the work order. Now, after the routing has been attached to the work order, there's a simple calculation of figuring out the average days per operation. And it's a simple calculation that takes the 10 days of fixed lead time, regardless of the quantity being ordered, and divides that by the number of operations. In this case, the calculation is 3.333 days per operation, or when rounding, it will use 4 days. So 4 days will be equally spread out amongst the 3 operations. Again, if the work order is due on 4/26, the routing step at the last operation will always start with a request date equal to 1 day before the requested date on the work order header. So the system, and in all 3 cases where we were making a work order for 1,000, 500, and 250, always plan to shoot to have the last operation done by the day before, which in this case is 4/25. If I go back 4 days, 1, 2, 3, 4, the start date of the last operation must start on 4/22 for it to be done by 4/25. If I use the same 4 days back scheduling through the previous operation, if 4/22 is when we have to start the last, the 4/22 becomes the requested date of the previous, and then from 4/22 go back 4 days. That's the 17th. That 17th ends up the requested date for the previous or the prior work center or operation 10, and then back schedule 4 days. That is the 12th. And so you can see when using the fixed lead time concept, regardless of the quantity you're using, you're going to spread out the operations equally amongst the fixed lead time days. Now, you should be careful when considering fixed lead times. There are some pitfalls. We'll cover those in a second, but you can see right away here that there's only 15 hours really needed for operation 20 and 30, but 50 hours are required for the first operation. So just spreading out the start dates and the request dates equally amongst imbalanced operations doesn't add up too good. Again, you can see when we make 250, there's 12 hours required, but we're still going to start on and request by 4 days. We're going to allow the first operation 4 days when really there's only 12 hours needed once we start the job. The next two, we're going to allow 4 days to complete the job, but it only needs about almost 4 hours. So you can see why variable lead time gives you a better picture of what your start dates and request dates need to be if we're going to operate a shop floor on a tight timeline and plan for all these materials at appropriate times. As I said, there are pitfalls to using fixed lead times for manufactured items, and one of them is capacity requirements planning. The plan and release hours aren't really going to reflect reality, as I just pointed out. And there could be cases where the materials we need at these operations, they may be arriving earlier than they're really needed, or in some cases, they may be arriving later than when we really need them. And then when it comes to completing these operations, because we're just spreading out the lead time across all the operations equally, you should expect completions at operations may be finished earlier in some cases than we expected, and in other cases, the actual completion dates may be finished later than expected. So again, you can kind of feel or get the feeling why the most popular lead time concept used for manufactured items is variable lead times. You get a better picture with your capacity requirements planning, more realistic load versus capacity, and the back scheduling helps materials arrive more when they're needed, and when you're expecting to complete things at operations and when you actually complete them can be tracked a little more closer. That concludes this recorded workshop on J.D. Edwards lead times and back scheduling logic. Thank you for your time. Now for the quiz. Each correct answer is awarded 1 point. There are 32 possible points and one bonus question at the end. The bonus question at the end is worth 3 points. You should strive to score 100%. Good luck with the quiz. Question 1 is 2 parts. Which is true and which is false? JDE offers 3 types of lead time concepts: takt time, cycle time, and lead time. Part 2 of the first question, JDE offers 2 types of lead time concepts. They are fixed lead times and variable lead times. Which is true and which is false? If you answered false and true, award yourself 2 points. Next question, number 2. Lead time options for purchased items can be variable, fixed, or both. You must decide which is best. Fixed. If you pick that, award yourself 1 point. Question 3. Lead time options for manufactured items can be variable, fixed, or both, but you must decide which is best. Both. You must decide which is best. Let's move on. True or false? The lead time roll-up program, R3822, is the program used to calculate item lead times. False. This is kind of a quick trick question. It's R3822A. Then checkmark each attribute that is used to calculate the lead time per unit. Take a moment, check mark the attributes used by R3822A. If you answered this way, award yourself 1 point. And another point if you got the true-false answer right. Next question. The lead time field for make items can be manually entered or system calculated. True. Then checkmark each attribute that is used to calculate the lead time level. Take a moment, review the list, check each attribute that is used to calculate the lead time level. If you got these attributes, award yourself a point and another for the true-false part. Next question. If a purchased item's lead time level field says 10 days, what does that mean to a buyer responsible for procuring the item? If you said our suppliers require 10 days to replenish material, you get a point. Next question, true or false? A purchased item's lead time cumulative value can be different from the lead time level value. True or false? False. The calculated lead time level value is copied and pasted into the cumulative lead time field when the lead time roll-up program runs. This is for purchased items. Next question. If a manufactured item's lead time level field says 10 days and the manufacturing lead time quantity value is 500, what does that mean to a planner responsible for scheduling the item? If you said a typical or standard lot size of 500 will require 10 days to replenish material, give yourself a point. True or false? Manufactured items' lead time cumulative value can be different from its lead time level value. That's true. The multi-level indented bill of material and routing structure's critical path is the cumulative lead time. But the lead time level value is only the days to replenish that item's single level bill. If you got these right, give yourself a point for each. True or false? The manufacturing lead time quantity value must equal the item's time basis code value. Example, time basis code 3, which equals hours per thousand. So the MLQ, manufacturing lead time quantity, must be 1,000. Is that true or false? False. But it is recommended to standardize these attributes using a rule to simplify the lead time inquiries. True or false? A manufactured item's lead time per unit value is only calculated if the item is using variable lead time concepts. That's false. It is always calculated but is informational only data when using fixed lead times. Next, true or false? The lead time per unit days value is stored in the item branch file, and users can look up this data in the item branch plant master. False. The data browser application must be used to view this attribute. Remember, it's not shown in the item branch application. You have to look it up in the file. True or false? The lead time per unit value represents the item's hours per each only. The lead time per unit value represents the item's hours per each only. True or false? False. The lead time per unit value is the hours per the time basis code used. An example, hours per 1,000 units if the time basis code was 3 for hours per 1,000. True or false? An item's critical path can be viewed using the item routing inquiry. False. The lead time inquiry must be used, not the routing inquiry. True or false? The lead time rollup program only uses efficiency percent for labor-intensive work centers and only uses utilization percent for machine-intensive work centers when calculating lead times. But when work order routing operations are back-scheduled, both efficiency and utilization percents are used when calculating its rated capacity for each work center. True. Give yourself a point if you have this right. Next question. Calculate the daily rated capacity when a labor-paced work center runs 1 8-hour shift and the number of machines is 1 and the number of employees assigned is 2. And the efficiency and utilization percents are both 95%. I'll give you a minute to calculate. If you got 14.44 hours per day, where you took 8 hours per day times 2 employees to get the gross capacity for this labor-paced work center, and then multiply it by the efficiency and utilization factors, then give yourself a point. Now calculate the daily rate. Now calculate the daily rated capacity when a machine-paced work center runs 1 8-hour shift and the number of machines is 3 and the number of employees is 1.5. And the efficiency and utilization percents are both 95%. If you calculated 21.66 hours per day, then give yourself a point. That formula was to take the 8 hours per day times 3 machines for the gross capacity, and then factor it by the efficiency and utilization. Next question, true or false? Rated capacity is used instead of gross capacity when backscheduling work order routing operations. True. The last operation on the work order routing and its requested date will always be loaded with a date that is the day before the requested date on the work order header. True or false? The last operation on the work order routing and its requested date will always be loaded with the date that is the day before the requested date on the work order header. True. Give yourself a point for each if you got them right. This formula is used to calculate what attribute? It calculates the lead time per unit. The R30 A22A lead time rollup uses this formula to calculate the lead time per unit. This formula is used to calculate what attribute? Lead time level. Give yourself a point. This formula is used to calculate which attribute? Work order days equal the lead time days plus queue and move days plus setup days. And here's the formula for each. This formula is used to calculate which attribute? Correct. It's used to calculate the start date of the work order header when the item is using variable lead time. Next question, true or false? When a manufactured item is using fixed lead time concept, the work order header start date is calculated by backscheduling the lead time manufacturing days from the work order header requested date and using a shop calendar. There's a spelling error there, but when a manufactured item is using fixed lead time concepts, the work order header start date is calculated by backscheduling the lead time manufacturing days from the work order header request date using a shop calendar. True or false? Hopefully you said false. Lead time level is used, not lead time manufacturing. True or false? When a manufactured item is using the fixed lead time concept, the calculated work order header, another spelling error, start date adds setup hours and queue and move hours when calculating the start date. True or false? When a manufactured item is using the fixed lead time concept, the calculated work order header start date adds set up hours and queue and move hours when calculating the start date. True or false? This is kind of a trick question, but hopefully you said false. The start date is calculated simply by subtracting the lead time level days value from the work order header requested date, using a shop calendar, of course. However, setup, queue, and move hours are used in the formula to calculate the lead time level days. So, if your answer was true, be prepared to explain. If you say only the lead time level days is used to backschedule the start date, but the lead time level days formula includes setup, queue, and move hours, then technically it is included when calculating the start date. I would award a point if you could state that case. But really the answer is false. The start date is calculated simply by subtracting the lead time level days, which already includes setup, queue, and move hours. True or false? When a manufactured item is using variable lead time concept, the work order header start date is calculated by backscheduling the lead time manufacturing days from the work order header requested date using a shop calendar. False. There's a formula used that leverages the lead time per unit days attribute. Here's a really tough question. We didn't dive into the details of fixed lead time concepts for a work order. We just covered them at a high level because variable lead time concept is the most popular lead time concept used. So let's see if you get this question right. When a manufactured item is using fixed lead time concept, the work order routing start dates and request dates are backscheduled using this formula. The first step is to calculate an average number of hours. It does that using a formula taking the lead time level value times the manufacturing constants, work hours per day, and then dividing it by the number of operations to get an average number of hours for each operation. Once you have the average number of hours for each operation, then each operation start date and request date are populated using the average number of hours for each operation's work center resource units. That is true. We didn't get into quite all those details, so I don't expect many people to get this answer true. But that is the formula used for backscheduling routing operations when using fixed lead time concepts. We're getting close to the end. True or false? When a manufactured item is using variable or fixed lead time concepts, the work order scheduling flash message can appear when the start date on the work order header does not match the start date of the first operation on the work order routing. True. Oh, I got that wrong. False. It was kind of a trick question. When a manufactured item is using variable or fixed lead time concepts, work order scheduling flash message can appear when the start date on the work order header does not match the start date of the first operation on the work order routing. This is false. This flash message work order scheduling can only occur when using variable lead times. When using fixed lead times, the start date of the work order header and the start date of the first operation in the work order routing will always be the same. You will never see a work order scheduling flash message when an item is using the fixed lead time concept. The start date on the work order header and the start date of the first operation on the work order routing will always be the same. True. Give yourself a point. What is the planner supposed to do when they see a work order flash message that is equal to work order scheduling? Nothing. Kind of a trick question, right? The job scheduler automatically runs the custom UBE called update parts list dates to synchronize all dates. Hopefully you did well, but here's a bonus question worth 3 points. Let's see if you can get the 3 points. What is the planner supposed to do when they see a work order flash message equal to operation scheduling? Are they supposed to do nothing? Are they supposed to manually change the work order header start date to the date shown in the start date of the first operation of the work order routing? Are they to run the custom UBE called update parts list dates? Or a shop calendar is missing, so go set it up. Or is the planner supposed to go set up the missing resource units? Number 5 is your answer. A work center is missing its resource units calendar, so you must go set it up. The system is unable to accurately calculate start dates in the routing because a work center is missing its resource units, or AKA work center calendar. That's what you get. You get a work order flash message called operation scheduling warning the planner, hey, I can't calculate routing dates correctly because there's a work center missing its work center calendar. Add up the totals of all the points you got right. Hopefully it's 100%. Maybe this bonus question got you to 100%. But users should study this PowerPoint recording and retake the quiz as often as possible until they get 100%. If you do that, you'll be well versed in lead times and will completely understand the calculations and how work orders are back scheduled.